Hello, my name is Tarun Mamidi. I'm a PhD student in Dr. Lesworthy's lab at the University of Alabama at Birmingham. Today, I'm going to talk about rare disease diagnosis without the need for human intervention using explainable machine learning and similarity matching approaches. The main goal for rare disease diagnostics is identification of one or more molecular variants causing the patient's phenotype. Whole genome sequencing is used to identify these variants, but typically we get around 6 to 7 million variants per patient. Going through each variant is a time-consuming process and is subject to reviewer fatigue. For this reason, I've developed two models, Ditto and Hazel, um, which uses both the genotype and phenotype information for a patient and identifies the causal pathogenic variant. For Ditto, I've downloaded reported pathogenic and benign classified variants from DBNSFP and annotated these variants with several annotations like allele frequencies from LOMAD, damage predictions from other damage prediction tools, impact from variant effect predictor, and so on. I've trained different machine learning classifiers on these annotations for variants and stack them to get a probability score for each variant as deleterious or benign. Along with a probability score, Ditto also gives explanations on why it thinks a variant is deleterious or benign. Figure 2C shows the feature importances for Ditto for each annotation or each feature, depending on the score for each feature. Let's say red is high score for these features, influencing the model towards deleterious than having low score, which is in blue, influencing towards benign. Figure 2B shows explanations for a variant that is classified as uncertain significance in CleanVar. Depending on the scores for each feature, Ditto influences predicts the variant to be either benign or deleterious. For the first feature, Ditto thinks this variant should be benign, but for the next couple features, Ditto thinks it has to be deleterious. Overall, based on all the features and their scores, Ditto thinks this variant is benign with a score of 0.013. Once we have deleterious scores for all variants, we are still left with hundreds of variants for each patient. To narrow down the search for causal pathogenic variant, we are using patient's phenotype information. I've developed a method called Hazel, which uses gene to phenotype associations extracted from the human phenotype ontology. For example, for gene 1, let's say we have 3 phenotype terms associated from the HPO database. Given a set of patient's phenotype terms, we'll map them on the ontology and use the common ancestors for each gene divided by the number of terms, number of patient terms, and get a score for each gene. Based on the scores, we will rank all the genes and then report back to the patient. To test these methods, I'll benchmark this on a database called OMIM, which has all the Mendelian diseases along with phenotype terms for each disease. I benchmarked Hazel with tools called like Amelie and Frank, where Hazel accurately predicted more than 99% of diseases to have a causal gene lying at the top of the list. Using Ditto and Hazel, we can first predict if a variant is deleterious with explanations, and then use the phenotype information to further rank these variant possessing genes based on patient's phenotype and report back to the patient as a diagnosis. These advances are of critical importance in the rapid, sensitive, and accurate diagnosis of patients with rare diseases. Thank you so much. Please feel free to say hello to me during the meeting.